Hello? Okay, let's hope it keeps working. Again, my name's Andy Nichols, and I'm a software engineer at Qt company. Primarily responsible for graphics and embedded. So my microphone's cutting out a bit. I've been with the Trolltech/Nokia/Qt company for 7 years. I've been doing Qt for almost 10 years. And, well, that's about a bit about me. Today's talk is Qt for device creation, which is now maybe if you've seen the product alignment where we have things now, things are split into application development and Qt for device creation. So this is more of the general a talk on the usage of Qt in that second domain, the device creation domain. What we typically think of as embedded. Okay, let's get this thing moving here. Move to the next slide. Yeah. Okay, so these are the things we'll be covering in this lecture. First, I'll start off by talking about some of the problems that we actually are faced in the domain of device creation. Then I'll talk about how Qt for device creation actually addresses those problems. In addition to that, I'll mention the boot to Qt stack, and if you've seen my talks in the last couple of years, that's generally what I was talking about. And so now I'll go over what that is in the context of Qt for device creation. And then we'll end things with some demonstrations. In addition to demonstrations, I also have some tips on actually building Qt for yourself for an arbitrary embedded device, so maybe something to look forward to. Okay, so let's move forward. So first off, starting out with the problems facing device creators, and there are a lot of problems that they're going to be faced with, but we'll focus on just the software side of things. So the first thing is actually finding a software development kit, something to actually build software for the device, then interfacing with the hardware, like what you actually need to obtain to do that, and then finding middleware to make that much more easier, and the tooling that actually goes with that. So just to dive right in, the software development kits for device creation. SDKs, or software development kits, consist of generally 3 big things. So first off, one is the system image that you're actually going to run on the hardware. So if you have a given device, you need a kernel and some user space, and something to boot it into. Then you have the tool chain, which consists of any of the tools that you actually need to build software for that piece of, or build software that can run on that system image on that particular piece of hardware. So that consists of compilers, like GCC and Clang, and then you need a sysroot. The sysroot is the development files that you actually need to build software for a given system image. So these are going to be things like the header files that you actually include in your C and C++ code, and then there'd be like the SO files, like the shared object files that you would link against. And these, of course, represent the versions of the libraries that are actually in the system image that you have. So depending on what operating system you actually choose, you're going to get your software development kit, different ways. The primary operating system we'll be talking about is Linux, specifically embedded Linux. And in that case, there's a menagerie of ways to actually get the software, but you're actually responsible for, acquiring that yourself. So one of the most popular ways is the Yocto project. So this is a standardization of the industry as a whole coming together to create a standard set of tools to actually generate system images and SDKs and sysroots. So that's actually what we'll be seeing later in the boot to Qt reference image. We actually use Yocto to generate the SDKs that we use. They also have build root, again, this is, like Yocto, a set of recipes for building each individual package that you need. So, it defines how do you build a kernel for a given piece of hardware, how do you build where do the graphics drivers come from if it, Freescale, I need to pull down from Freescale servers and, extract those binaries into my SDK. Basically everything you need to build for a given system, it will build everything from scratch in that case. And then you also have the option, or sometimes you get a piece of hardware and you don't have the ability to build your own software for it. They've just given you a Ubuntu image that they've modified, an ARM v7 Ubuntu image that they've modified with a few extra packages. And there, that is your SDK. Ubuntu is your SDK, and you have to find ways to, build your code, against, ARM Ubuntu. And this also brings up the topic of board support packages, or commonly abbreviated as BSPs. And these are going to be things provided generally by the hardware vendor that you're buying the hardware from. So, if you're getting, say, a Torex board like we're giving away, that particular board has an IMX6 SoC, and that's Freescale. So you look for the Freescale BSP, and that'll provide things like Linux kernel patches, so you can build a given kernel with any additions that they need for that piece of hardware for things that they haven't upstreamed yet. Things like graphics drivers, like most of the graphics drivers for embedded hardware are actually proprietary. There's no open source, MISA backend for these things. So you need to get the graphics drivers from the vendor. And then other things that are commonly proprietary are radio hardware. So, GSRM or GSM, NFC, Bluetooth, those things are going to be closed binaries in many cases as well. In addition to regular Linux, there's also the Android variant of Linux. And in this case, if you're building for Android, then rather than using Yocto, you're going to use the AOSP, or the Android Open Source Project. It again uses the same Linux kernel, and the advantage over embedded Linux is it's a standardized platform. So hardware vendors can build to a certain graphics and multimedia API and provide those integrations there. So if you're able to use Android as your embedded platform and your hardware vendor only provides those additions, then you'd be able to just use those potentially pre-built images from the hardware vendor, and then to actually build software. So the tool chain and the sysroot, they actually come in the form of Android's or Google's Android SDK and NDK. Another very popular embedded platform is the Windows embedded, the Microsoft's offering. And that's a bit different than the other two because generally it's up to your hardware vendor, or in many cases your hardware vendor will actually do the integration with the Windows embedded image, so maybe kernel patches and things like that. And then your customization comes down to what modules you're actually going to include, what parts of Windows embedded you're actually going to include in your end image. And the SDK comes from Microsoft. And then, maybe not as common as the other, but still quite valid, is the R2Ss like QNX, VxWorks. And in that case, you're going to have to generally go through, the R2S provider to get those customizations, and that, can sometimes come with consulting work and can get quite expensive, but, sometimes that's necessary. But as far as where the SDK actually comes from each given platform, I think that gives a kind of an overview. Depending on what platform you actually pick, you're going to obtain the different parts of your SDK in different locations. So the next thing, the next problem facing device creators is actually interfacing with device hardware, because it's one thing, to be able to, boot up the Linux kernel on an arbitrary piece of hardware. Next thing is, okay, my user space application, I want to access those peripherals. So, things like cameras and sensors, if you're, collecting data, or using the GPU if you're processing data, or, putting things on the screen. And then, other things like audio output, multimedia, radio, like all of these is individual device hardware that needs, extra effort on your part in your end application. So this is kind of how the stack works. And in this case, we're actually, including Qt in this. So you write your application with Qt, and by using these Qt APIs, then for each of those given platforms, we write, or the Qt libraries actually provide native interfaces. So in the case of Linux, if we're talking to a particular device, maybe we're actually talking directly to that block device or that character device in the platform native interface, and then translating it to something that you can actually use in a cross-platform way from that Qt object. So things like playing multimedia, you don't have to worry about the intricacies of actually playing audio on Linux. So for example, you don't have to know anything about ALSA to actually play audio. We'll handle the messy details of each platform for you. So again, since you'll be wanting to interface with that hardware, and you don't want to deal with each of the very detailed interfaces that you interact with hardware, whether it be kernel ioctls or again ALSA. You want some good middleware, and of course Qt provides that middleware, and it actually has a very large scope. I'm sure many of you are familiar with Qt, but in the case of embedded, we provide user interface primitives. I think that's the most common thing that people think of Qt is widgets and little Qt quick controls. And of course the idea there is making it very easy to convert your designer's vision into a user interface. But there's other important things that you might not think about until actual implementation, like internationalization. If you're trying to ship your embedded device or application to countries that don't just use Latin 1, then you're going to have to take that into consideration. Other things like input methods. Embedded devices don't necessarily have hardware keyboards or hardware buttons at all. So if they're just a touchscreen, you're going to have to think about virtual keyboards or remote controls, so 5-key navigation. And then we have very high-level primitives like you want a web browser, so you want to run HTML5 content on your embedded device, or you want to play back videos. So the Qt middleware would provide those things as well. So again, the scope of Qt is quite huge, and in the embedded space, this is also the same kind of things that we're supporting on the desktop. Are also working on embedded, and they're also the same kind of things in a modern embedded or product that you'd actually want to use. Okay, so that pretty much sums up middleware. Qt provides a lot of APIs that you actually have access to when creating a device. But that only gets you so far, because you also need good tooling to go along with that, because not all of us only program in Emacs or Vim. I know traditionally when I was doing embedded devices, it was a lot of using the serial port to talk to it, and basically doing everything and everything over the serial port, or sending things, putting them in the SD card, very manual process. But, in the post-iPhone world, the post-Android world, those are embedded devices. iPhones and Android phones, those are technically, embedded devices, and it's very easy to, develop software for those devices, and there's very good tooling to go along with that. So it's very important to us that we also provide that ease of tooling. And we do that by providing a IDE, and that's Qt Creator, and I'll be demonstrating that in just a little bit. I mentioned, the ease of deployment to devices. We want, when you're deploying to software or deploying to your device, we want it to be, just as easy as it is on the iPhone. So one click, we build, we deploy, it starts running on your embedded device. Same thing with remote debugging, remote profiling, and in the case that you don't actually have an embedded device, we'll also want to provide a simulated environment that, this would be an environment that's running the same, system image, but, on your desktop that you would be running on your embedded device. Good. So yeah, so Qt Creator is the IDE which I mentioned, and that's the QML designer, which I'll also show in a little bit. And in the device creation workflow, modern embedded devices, or if you're not developing something, without a screen, is going to be generally going to be a touch device. And Qt was designed for this embedded touch-friendly world. And this is the workflow with that is, you have your designer comes up with some crazy user experience, and, you want that to match as closely to what they put in Illustrator that you put on the device. So, designers and developers working together with Qt to do that, and, that's done in Qt, and then all of the business stuff, all the actual work, that isn't, just your UI dancing around and, pinch zooms and all that. That's actually done in C++ with the Qt C++ libraries. And you can kind of see that there. And there's a way to bridge that gap, and I'll be showing that as well in our demonstration. Okay, so before we get to the demonstration, I'll talk a bit about the boot to Qt pre-built reference stack. Again, this is what I've talked about in the past. This is our, it's hard to get started with embedded, so let us, get you started with embedded. So what we did with the boot to Qt stack is actually provide a set of reference devices, like commonly available commodity embedded hardware, and, make images available through the Qt device creation offering that you can, flash to an SD card, put it in your device, boot it up. It boots up to a launcher, just to show you what the device is capable of. And then we also give you the SDK to develop software for that device. So, the tool chains and the sysroot that you actually need. And then have Qt Creator configured to already deploy to those devices. So, and a little bit about this boot to Qt reference stack. It's a lightweight Linux stack, so basically the bare minimum that you need to build Qt with all of the features enabled. And we're not using X11, a bit heavy for the embedded devices, and we want to be able to use OpenGL, so we're using the OpenGL, the OpenGL ES, what's it called, EGL full screen plugin. And that interacts directly with FBdev in most cases. And it's a fairly, compact reference platform that you can also use to, get started, start doing your development on very similar hardware to what you're, intending to use anyway. And then you can even go back and customize that image and take things out, add things that you need. Of course, I said you can, we have lots of reference hardware. I think there we have, that's one of those compute on module things that, actually that is the one that they're giving away today, the Calabri IMX6 Dual Lite, that little chip, and there's a little carrier board that it comes with that you plug it into. And then this is another IMX6 device. I think that's a Boundary Devices one. And I actually brought an IMX6 of my own as well, so I have that. It's going to be hard to see, but you won't really need to see this one just to know that I have actual hardware running here, and it has the boot to Qt reference image on it. We'll deploy some software to it right now, because, it's demo time. So let's jump into that. Okay, so I'm going to switch over here to my Linux machine. This is Ubuntu Linux. And what I've actually done is I have a simple application here. But first, I just want to show you how easy it is to, go from, complete nothing to an application, and then we'll go ahead and edit an existing application. So first, in Qt Creator, it's a bit small, but what it actually says is, new file or project. So I'm just going to go ahead and do that. The typical Control-N. And then we're given a list of application types. I'm going to choose a Qt application because we're making an embedded application here, and we'll give it a simple name like test4. 4, and version of Qt, the latest version, of course, because why not? And here you actually get a selection of kits. And kits in the Qt creator world actually reference it's a combination of a platform and an SDK. So, well, in the Qt case, it also includes a Qt version. So, since we're actually going to be deploying to this boundary devices IMX6 kit, I'm just going to go ahead and click this one here. That's what it says, boot to Qt 5.5 embedded Linux boundary devices. I'm going to uncheck all of these other ones because I don't have them with me. I have a lot of devices, or a lot of Qt versions. And we'll do the emulator as well because, I want to show you that. That's cool. And, yep, that's it. So let's just do a desktop one as well, just because, so we can see what the desktop version looks like. And then we'll just finish it out. And it looks like here it's just going to create a simple QML designer form. And if we click on that, it should open up designer. And in this case, it's just a simple white program with a hello world. So if we run that on the desktop, it looks like this. Probably just a 360 by 360 window in white, which is fairly small. But that's it, really easy on the desktop. But of course, most of us in this room have done that before, so no problems there. Of course, now I want to run that on my embedded hardware. Here, you can kind of see it's not running a Hello World application right now. But if I wanted to run on that hardware, all I would need to do is switch to the Embedded Linux Boundary Devices kit here. And again, this is one of the pre-built stacks. So only thing that I've done on my side is flash an SD card with the image that came with this kit. Like we have a flashing utility where for any of the installed reference images you have, you actually open up the flashing utility, you get a boot wizard to say, oh, put in your SD card, what image do you want to flash to it? And I picked IMX6, Boundary Devices IMX6. But now that it's actually hooked up, I have it hooked up to my laptop via this standard USB cable that you use to charge your phone. It's the USB on the go port, I suppose. And you can see here that it's actually connected, it's talking to it, so I'd be able to deploy to this device that since it's already been configured, and building and running it is just as simple as hitting run. And yeah, it's already running actually on the device, so you can kind of see it's white. But of course, since that's so tiny and it's hard to see, I want to show you the other really cool feature, which is the emulator. So let's do that. That itself is just another kit, and if you don't have hardware, then it's very simple just to use the same reference stack in the emulator. And to start the emulator, I just have to hit that button here. It's going to boot up like any other embedded device, so posting a lot of crazy kernel text to the screen. And if we just wait a few seconds, it should get itself started. So now it's actually booting into the same demo launcher that it would boot into if this was on the embedded hardware, since it's the same image. And of course, this is also using OpenGL ES2 to render what we actually have. So if you want to test out the virtual keyboard, you can do that here. But since we just wanted to run our application, now that I have the emulator kit selected, just hit run here, and it should pop up on this screen. Yep. And really, that's all there is to it as far as like running demos goes. So, of course, hello world examples are lame, and especially white rectangles with the words hello world in them. But so I have another example that I have done. It's a simple user interface for displaying and editing. It's a terrain generator, basically. So I'm going to run it on desktop just to let you see what it looks like in all its glory. So I'm just building it for Qt 5.5 for X11. And yep, there it is. So here's the application that will actually be running on our embedded device. There's a very simple UI itself. So you have some controls here that let you modify the variables of the terrain generator. So on this side, you can see there's some water, and you can see the depth, and then you can see the land, and you can move it around. You can zoom in and out and see what it actually looks like. So it's just a very simple application that has both a visualization and the ability to actually control what's going on. So you can kind of see that this would be, while this is also kind of contrived, it might also represent the kind of HMIs that you'd have, in an embedded device, where I'm just going to be touching these buttons here, like the zoom level buttons, to move, another control around, or setting some parameters with some sliders. And so we can run that also on our embedded device. I'm going to go ahead and just run it in the emulator again, because we already have the emulator open, and you can actually see the emulator, and it's not 7 inches and 20 meters away. So we have nothing running on the emulator now. I'll run my application there. Yeah, so we're running the same application on this embedded device now. It's a touch application. And I guess I can show you a little bit about this application itself, because we want to extend this application. We want to add additional controls to this application to, interact with more variables that we may have with our terrain generator. So the first thing is we can look at, the actual code for the application. So again, this is a QtQuick application. So, that means it's a C++ and QML application. So on the C++ side, this is the main entry point. If you've written Qt applications before, this will probably look pretty similar, because you instantiate the QGUI application, and then from there, we're using this QQML application engine, which I've just destroyed, to instantiate our QML file that has all of the logic for our UI. And the only thing, most of the stuff is done in QML, but we do have some C++ that we instantiate from QML, and that's actually done here, or we're actually defining, exposing a type, a C++ object to QML here. So in this case, I have this terrain viewer item, which will actually be the item that actually displays the terrain. So all of the procedural generation of the texture that gets shown in the GUI is actually done from C++. So, and that's what we do here. So this terrain viewer item is actually our C++ interface. And in the actual GUI, it's a very simple GUI, because it's an application window, just single full screen application. We even have here where we set the properties of the screen to always be full screen. And then we instantiate this main form object, which again is another, if you look over here, it says it's a UI file. It's kind of tiny, but the UI files actually mean, the UI.qml actually means that it's a QML designer file. So I've actually made the GUI using the drag and drop QML designer editor. And we've instantiated that, and then the C++ item here that gets anchored to the inside of the form. So if we open the main form.qml here, you can see what the user interface looks like as a preview. So I've drug and dropped the controls that I wanted into the layout that I wanted it, and now I can visually edit additional things here. So if I want to extend this GUI, it's fairly trivial. It's just a matter of dragging and dropping. But the actual goal of this exercise is to add an additional control that will let me set a Boolean property on the terrain generator to get rid of the gradients. Because when we actually run the application, you can kind of see that higher mountains look, like the higher elevation is darker, the deeper the depth in the ocean, the darker it is. It's kind of hard to see there, but it does have. But that's process intensive, so it's it's not something we necessarily want on our embedded device. So in able to get it running faster, we're going to dumb it down a little bit. So I'm just going to show you how to both extend the GUI and extend the C++ backend to make that possible. So if you actually look here at what we've done so far to expose the the sliders, the things that are actually modifiable in the user interface to the C++ backend. You can see we're moving the slider here. That's actually done here with the property bindings. In this case, the terrain viewer form has a object called water level slider that we then take the value from and assign it to the water level property of the terrain viewer item. And if we actually look at the terrain viewer items header file, again, it's a C++ class. In this case, it's a QQuick item subclass because it's going to be a visual item to see. You can see here that we have properties using the QProperty macro that basically defines the getters and setters for a given property and how it's exposed to the script context, or in this case, QQuick. So we have a water level property. So then if we want to bind anything in QQuick to this property, or this is the property, the name of the property that we actually use to make those bindings from QQuick. And QQuick itself will call the set water level when needed, and if we change it from C++, it'll emit the signal water level changed, and then again they're bound in the same way that you'd write QQuick stuff. So if we actually want to add a control, what we do is we're going to go to the main form, and we're just going to add a simple mode checkbox. So I'm going to drill down to the right place here and just put this into the form. Checkbox. You can see it there. We can give it a name, or we give it a text. We'll say simple mode. That gets updated. And then I kind of want to have this into the right layout. So I think it's the controls containers where it actually needs to be. Yeah, this is it. Yep. So now it's actually in the layout. So it'll get positioned correctly if we resize the UI or at least use it on a bigger screen. And then I think the last thing we need to do is give it a decent name. So let's go ahead and give it a name. We'll call it simple mode checkbox. And the other thing we have to do is, because this is generating QML behind the scenes, and we want to access it from outside the form, we need to export it globally. So we can click this button here, and then it'll add an alias for that. So if we actually look here at the generated code, you can see the simple mode checkbox then gets a top-level alias that we can reference in the main.qml file. So now that we have that, we have the control. If we were to start up the UI again, and we can go ahead and do that, we'd have it, but it wouldn't do anything. So let's start it back up in the emulators. We have a simple mode, and we've extended the UI, but now we need to hook it up to the C++ backend. So first, before we can bind it to anything, we actually need to add the property in C++. And so normally that's a lot of boilerplate code because, you got to have a getter, you got to have a setter, you got to emit the signal at the right time. But we can actually do the cool trick of, just using QCreator to our advantage. If I would type right, I'm going to type QProperty, and QCreator automatically fills in the things I need. I just need to set the type. In this case, it's a bool. The name is going to be simple mode, and hit enter, and we have this part generated. And if we right-click on that and go to the refactor tab, we can actually have QCreator generate the boilerplate code that we actually need for the getters and setters. So if I click that here, then it will add, the getter, and then down here the setter and the signal. And if you look in the actual implementation of this, it has the emit simple mode changed whenever this happens. So I'm going to go ahead and refactor it again and make sure that this gets sent to the CPP file because, it's messy to have inline implementations in your header file unnecessarily. So I'm just going to do that real quick. And then that's basically the only thing we need to do to expose the property to the UI. So now if we go to the main.qml file and add an additional binding here, simple mode, probably haven't picked up on it yet, but we can terrain viewer form, simple mode checkbox dot checked, yes. And now the UI has it bound to that property. Of course, it doesn't do anything yet because, it's just a Boolean property, but we can hook that up to the terrain generator. If we look at the terrain generator method, there's actually a simple mode Boolean at the end of it, which of course, I did earlier to make it, a lot less complicated on our part. But If we go to the actual place where the terrain generator is called here in the, this basically gets called anytime anything changes in the UI. We just need to bind the property of the simple mode here, and now it should be actually doing something when we change it. We do have to do one more thing, and if you see for the other properties that you change, like set Y location, so when we're actually hitting the left and right buttons, we're having to call request updated image, so we just have to make sure that whenever you hit the simple mode, we want to redraw the UI. And now if everything's right, we should have simple mode checkbox working, so I'm going to go ahead and run it and hope for the best, because live coding is dangerous. So that's not a very good place to look at the actual differences between light and dark. Yeah, you can cut it. You can see light and dark there. So now, if we're lucky, if we click the simple mode checkbox, it should go away, and it does. Cool. So that's really how easy it is to extend the C++ backend to do certain things, and I guess the point of this exercise is to make sure that you understand that most of the stuff you're going to be writing for an embedded device is going to be in C++, but your UI is going to be in QtQuick, and you need to be very familiar with how to bridge that gap, to keep most of your, actual logic in C++, despite the temptation to write everything in JavaScript, which will just turn out awful on an embedded device. Okay, so a couple other cool features that, we have. I mentioned, remote debugging. You can do that for both the C++ and the QML. So if we were having problems with our terrain generation, so we could actually set a C++ breakpoint here where we actually generate the QImage that we display as a texture. And now if we were hitting debug, it's going to start up our application in the emulator. And it's got to load up the debug symbols first because, we want those. And, now we're able to remotely debug to our embedded device. And maybe it's not so impressive if we're doing it in the simulator. Let's switch back to doing it on our actual device because, that's how badass we are. All right, here we go. Let's do it on the embedded device. And, you can definitely tell the difference, even if you can't see very far, that is obviously not the application we're trying to run. That's just some white Hello World application. And we're still loading up the application's debug symbols now. And probably we won't see anything as soon as it actually gets going because it's going to break before we even get the first texture on the screen. Okay, but it is still loading. You can see down there at the bottom, it's actually going through each SO file and getting the debug symbols. Okay, so now we've actually hit our breakpoint, and you can see in the UI there's a big black box where our texture should be because we haven't generated it yet. And, we're remotely debugging on this device. We have a full backtrace here. We have the locals over here. We can drill down and see things if we really wanted to. In this case, it's a QtQuick item, so there's nothing interesting to see. We can drill down in here and actually go through the terrain generator code. It's got to, get to it. We can see, how that actually worked if we wanted to, if we were having problems with what actually got generated. In this case, it's going to iterate through quite a big, array of pixels, editing each one as it goes. So we probably shouldn't do that. The other thing, you'd also be able to debug the QML side. So if we actually got rid of the breakpoint, and I don't know if I did already. No, I didn't. And we were just to run this normally as a regular application. And we'll have to wait for it again. I don't think I hit the right button that time. No, I didn't. Hit the debug button. Again, we don't have any C++ breakpoints set, so we're running in GDB. And if we seg faulted, we'd get, an entry point there. But we also starting the QML debugger. And the QML debugger, it's, a different context there. It's, JavaScript and the declarative QML or QtQuick language. So that's going to take a little bit of time to get started, it seems. And yeah, there it is. So now you can actually see in this view, in the locals view, we're not actually stopped, but we have access to the locals view. And this is actually the QML property hierarchy in real time. So if I were to actually dig down and find something interesting like the terrain viewer form, maybe the, what's happening? Oh, it's getting all dark up there. Let's see, do we have any value property? Okay, so here's the properties for these sliders. So it's kind of, yeah, you can kind of see there, water level, snow level, zoom level. And if I were actually to change the snow level here, oh, if I could touch the, yeah, I can touch it. You can see that it's actually changing in real time as I'm moving the slider. And you can see how that, might be useful, to see things in your user interface happening in real time, make sure the binding's actually there. You'd also be able to, if you actually set breakpoints in QML, like in some of the JavaScript event handlers, it would break there as well and let you see, the stack at that point. Okay, and the other cool thing is the Analyze tab. This also works in the embedded platform. So, and we have the QML profiler here. So, if I wanted to figure out why my application was sluggish. So, if it was sluggish when I ported my QtQuick application to my embedded device, I could actually run the QML profiler here on the UI and see how it was working. So let's see, I'm moving around in the UI here, and I can stop it, and it will give me like an analysis of how the performance was there. So you can see things like the PixMap cache, like what assets were actually loaded. You can see the memory usage, and so as things are declared, you can see what declared them, how much it grew, and like you can see how big the memory allocations are at any given point in time. And you can see all kinds of things. I mean, the scene graph rendering, so you can see, when it actually does start rendering, like in this case, you can see each part of the scene graph render loop and see, are you really, keeping in your 16 millisecond budget so you can hit 60 FPS? You can go through that and see what's actually, preventing me from rendering at 60 FPS. Or other things like startup time. If you're optimizing for startup time, in the case of QtQuick, you have this compilation phase where each of the QtQuick items need to be, or the JavaScript items need to actually be, compiled at runtime. So you can see how long each item actually took. In this case, it's the styling components. A lot of the styling components for the actual, drawing the sliders are getting compiled here. And of course, there's many things to actually drill down on, like the JavaScript, what JavaScript was run, how long did it take the bindings to run. You can really go through every little thing that happens in the QtQuick interface. Yeah, so we also have support for some CPU profiling, like in the case of the embedded device, this is going to be the O-profile style, polling CPU profiling, because if you're running like Valgrind on an ARM device, I mean it's potentially slow enough already in debug mode, and you put it in an additional layer there, you're going to have quite a bit of trouble. But okay, I think as far as demonstration goes, that's what I have for that, and then we'll move to come on, go to the next thing. Yep, there we go. So building your own version of Qt, however you got your SDK, maybe you didn't get, Qt as part of your SDK. You're not using boot to Qt, the reference stack. You have Qt from wherever. So you still need the same things. You still need a tool chain that you can build C++ software with. You still need a sysroot from somewhere. In the case of embedded Linux, Yocto or buildroot will generate, the image and the SDK. And you have an image to deploy to, or you have an existing image to deploy to, like say for example a Ubuntu image running on a piece of hardware. And here, there's a bit of a distinction between what is your host machine and what is the target image. This is important for Qt because when you build Qt, you're not going to build it on your device. I mean, it's crazy. It will take so long. I mean, some of these new ARM devices are pretty powerful, but still, you're talking hours as opposed to 10 minutes. So, you need to know what architecture your host machine is and what architecture your target machine is. Okay, so then it comes down to configure. So one of the great things about Qt is the QMake build system, and QMake, like once you've run configure, QMake knows everything. So when you're cross-compiling, if you just run QMake and make, it already knows that you're building on an x86 machine for an ARM machine, and it's going to generate things with that assumption in mind, and you don't really have to think about setting any additional variables. The only time you have to set variables is when you build Qt, and that's when you're running configure. So if you're building for an embedded device, these are the configure variables that you actually need to be worried about, like for anything. So the first one, is one you're going to recognize because that's something you're probably already using already, is prefix. And in the case of an embedded device, this is the target folder that you intend to be deploying to. So in this case, user local, if that's where you want to install your Qt libraries to. So if you want it in user local lib, that's your prefix. Then you have the ext prefix, and this stands for external prefix. This is what the location on your host machine you'll actually be installing the Qt libraries to when you run make install. And this is almost always going to be inside of your sysroot. So the ext prefix will look at whatever your sysroot is located that you're building against, /user/local. So it's sysroot target prefix. I mean, there are very few circumstances where it will be something other than that. The next is host prefix. Host prefix is actually where it's going to install any native tools that it's building. So you think of things like QMake. While you're building Qt, where you're configuring Qt, you're actually building for both x86, 64, and your target architecture. So any of those variables that are meant, or any of those binaries that are meant to be run on your build machine, that's where they're going to be installed. And that could be, your own preference where you like to install things. So just think about where do you want QMake mock and UIC. You also have the sysroot variable, and that should be self-explanatory. Wherever your sysroot, wherever the development files for your system image get put or installed, that's what the sysroot variable is for. And then the final thing, which might be a bit different, with Qt 5, we've introduced the concept of device make specs, whereas before you would set the make specs based on -platform, the platform you're building from, and -x platform for cross-platform, which platform are you targeting. In the case of device, this bundles a lot of that configuration that you actually need and includes things like the hooks needed to do OpenGL-ES. And for many common devices, we've already provided device make specs. So if you just say something like -device Raspberry Pi, it will automatically build for Raspberry Pi for you. And the thing that's different about this is that you do need to set this device option, in this case the cross-compile variable. So if you use device Raspberry Pi, then you need to also say -device option, cross-compile equals, and then the location of the cross-compilation toolchain. So wherever the GCC version is located that actually builds for ARM, that's what you need to put there. And then once you've done that, it'll build Qt, it'll build QMake, and you'll be set to go. Okay. All right. One last thing, and then I'll have to stop. And that is, once you've done all that, how do you do the same things that I was just doing in Qt Creator? So I can show you real quick how you create your own kit in Qt Creator. So if you built your own version of Qt, you have your own toolchain, your own sysroot. Here's how you hook that up. So you just go to Tools, Options, and then go to Qt Build and Run. And here's where you actually define your kits. So you can see from the tabs up here, it's listed debuggers, compilers, Qt versions, and kits. So what I like to do is just start down here and define each one of those things. So in the case of the debugger, I would hit Add, and then just give it a random name. So, IMX6 debugger. And then if you have a version of GDB that supports, talking to remote ARM things, you just find that binary. And this is going to be generally in your toolchain folder if you've built GCC in the same places. So your host tools, toolchains. So the same places that GCC is actually going to be. Same thing for the compilers tab. The only thing you have to do for a compiler is, again, add, tell it it's a GCC compiler if it is, and then give it the path. And really the path is just find GCC or G++ the cross-compiler version. So if you have a Raspberry Pi toolchain, just give it that GCC, the location of that GCC, and everything else gets filled in for you. Qt versions, to add a new Qt version, including cross-compiled Qt versions, it's just a matter of hitting add and find the QMake binary. So when you build Qt, in that previous, the tab, the host build tools, QMake's going to be in the bin folder of that. So if you just add that QMake, it knows already that you're using GCC for Raspberry Pi, you're using Qt version 5.6 compiled to remote or to cross-compile to ARM. All of the stuff's already there for you. And then once you've defined those three things, you add a kit, and then just define, okay, here's my debugger, it's this one. Here's my Qt version, it's the IMX6 one that I built, and where's the other one? The compiler, yeah, so you set the right compiler. And then, that basically sets you up to build, but then you need to be able to deploy. And in that case, you need to set up a device. So in this case, it just says device here. You say manage, and then you add a device and basically define how do I deploy to that device. So whether that be, you generally, over SSH, you just define, okay, what's its IP address, what's its host name, maybe push an SSH key to it. And then once you've done that, you can add that device in your kit, and it'll show up here. And then you'll be able to, it'll not only cross-compile for your device, but then allow you to deploy directly to that device and run to the device and debug on the device if you've provided all of those things. And that's really all there is to it. Okay. I think that is it. So, thank you very much. I'm going to open the floor for questions now. Yes. We have a few minutes, I think, for a few questions. Yes, so you first.
Yeah, so what I'm thinking about is that this whole process is a lot like you have two separate decks of cards. Like you build your Yocto image, and that's the one you have to start, and then you build a Qt design, and then you shuffle them together.
Oh yes, so you did bring something up that I neglected to mention, and that is that this is only if you're in a scenario where you're not, because you could just as easily have built Qt through Yocto, and those same steps apply for the most part. Setting it up in Qt Creator, so. The configure steps that you saw there, you don't even have to worry about, because in the Yocto case, those are actually filled in for you when it builds the Qt5 projects. So you don't have to worry about configuring Qt. It does it for you. Only thing you have to do is hook up QMake and the compiler and, basically the SDK in Qt Creator.
So what I was going to get to is that I think Lars mentioned something like better Yocto integration or collaboration.
Yeah, so we...
Can you talk a bit about the roadmap for...
Oh, and right now, so we are actually contributing patches to the MetaQt5 project now. So our intention, of course, is to make it as easy as possible to build Qt in any build, in any build settings, or whether that be, Yocto build root. We want to make, as Qt as accessible as possible.
Is there something we can look forward to in 5.6?
I think I think 5.6 is the release. So the next release of Yocto, the meta, I can't remember what the name of the next release is for Open Embedded, but Qt 5.6 I think is what the target is there for that. So with Qt itself, with the commercial version, we actually have we distribute a copy of MetaQt 5 that will build Qt, so you can use our version of MetaQt 5. But then in the next release of Yocto, we actually have the patches in there, our additions that actually make all of this possible as well. So a lot smoother experience with using Qt in Yocto with MetaQt 5.
What about providing a little meta layer for the enterprise extensions, like the virtual keyboard, so we can get...
So that's what we actually have when we distribute our version of MetaQt 5. We actually have those additions already in there. It's just, because of the commercial, it's kind of hard to get the code with the open source MetaQt 5 layer. So we're trying to solve that problem as well to make it as smooth as possible. But right now, even with the latest Qt for device creation release, we actually provide that MetaQt 5 layer that has those extra recipes for building the commercial editions as well. Any more questions? Yes?
How do you define the emulator for this device?
So right now, the emulator that you actually see there, I don't think it's possible to customize that. That's just the boot to Qt reference image being booted in that. But I mean, in general, I mean that is it's an x86 emulator, or it's a VirtualBox instance. So it's not it's a simulator more than it is an emulator. We're not running QEMU or something like that. But okay, I think that's might answer it. Any more questions? I don't. Oh, yes, you again.
It's nice and great having Qt up and running on these embedded devices, and I guess that's kind of you and your team working on that. But how are the other teams contributing? Are there kind of the scene graph people trying to look at some specific optimization?
Oh, I mean that's what we.
Or kind of IO.
It's what?
IO or memory RAM, so that your OpenGL performance is often limited by the memory.
Yes.
And all of the optimizations in the scene graph are that you can enable caching everywhere, and that's just going to destroy your bandwidth even more.
Yeah. Well, I guess in our case, the scene graph guys are also the embedded guys for the most part. I mean, there's a lot of overlap there. But, I mean, yes, that's what we do look at. I mean, primarily, like, our focus is, making the graphics work well for specific embedded devices as much as we can. I mean, we try to stick to the most commonly asked for devices by customers. So, you see lots of IMX6s because that's what people are asking about. But, I think. Well, as far as that goes, I mean, we don't necessarily see that as our place either to mess with things that, aren't cute. So, those are like, if you're getting your image from TimeSys, or that's the kind of that kind of domain, or your case and your consultant's case, for optimizing for this. Like, we can only do so much inside the Qt domain, and we try to keep it that way. So, or we try to do what we do best, and that's things in Qt. And if we're bound by something else, we can only do so much other than complain complain on their mailing list. Well, it depends. It's I could say, that's the answer for every question in embedded is it depends, because, with the kernels, we're typically limited to if we want to use this, if we want to use the graphics drivers, we only have 2 kernel choices to begin with. So, all right, I think that's all the time we have for questions. Of course, you can hunt me down. I'll be here the next 2 days, so just come find me and ask me questions in person. Yes. So